Welcome to Star Technology 5G. In this tutorial I will show you the introduction to TCP over IP. Let's start the video. Introduction to TCP over IP. Just like human beings we communicate with each other, it's important for computers to have a common way to communicate with each other. Computers can perform any communication in a network only when they agree to a set of rules applicable to every computer. The set of rules that governs the whole communication in a network are called protocols. So, the standardized rules that allow any computer in a network to communicate with each other are called Transmission Control Protocol over Internet Protocol, TCP over IP. TCP over IP can help in developing communication between two computer systems, which make it possible for you to browse any websites, send emails, and start online streaming. When two computers want to communicate with each other, they should follow the rules. These rules should be same for both computers. For example, if this computer want to send message to that computer, then he should follow the protocol, step 1, step 2 and so on. Other side he will understand the same protocol and accept the message. If both computer do not follow the same protocol, then communication will not establish, and they cannot communicate with each other. History leading to TCP over IP. Today, the world of computer networking uses one networking model, TCP over IP. However, the world has not always been so simple. Once upon a time, networking protocols didn't exist, including TCP over IP. Vendors created the first networking protocols. These protocols supported only that vendor's computers. For example, IBM, the computer company with the largest market share in many markets back in the 1970s and 1980s, published its Systems Network Architecture, SNA, networking model in 1974. Other vendors also created their own proprietary networking models. As a result, if your company bought computers from 3 vendors, network engineers often had to create 3 different networks based on the networking models created by each company, and then somehow connect those networks, making the combined networks much more complex. Although vendor-defined proprietary networking models often worked well, having an open, vendor-neutral networking model would aid competition and reduce complexity. Example: IBM create its own network card and Dell create its own network card. These network cards only support that vendor. The International Organization for Standardization, ISO, took on the task to create such a model, starting as early as the late 1970s, beginning work on what would become known as the Open Systems Interconnection, OSI, networking model. ISO had a noble goal for the OSI model, to standardize data networking protocols to allow communication among all computers across the entire planet. ISO worked toward this ambitious and noble goal, with participants from most of the technologically developed nations on Earth participating in the process. During the 1990s, companies began adding OSI, TCP over IP, or both to their enterprise networks. However, by the end of the 1990s, TCP over IP had become the common choice, and OSI fell away. Proprietary networking models still exist, but they have mostly been discarded in favor of TCP over IP. The OSI model, whose development suffered in part because of a slower formal standardization process as compared with TCP over IP, never succeeded in the marketplace. And TCP over IP, the networking model originally created almost entirely by a bunch of volunteers, has become the most prolific network model ever. How TCP over IP works. TCP over IP is a communication protocol that establishes a connection with another computer and ensures that the packets are sent and received successfully. Every message or data that is sent in a network breaks into multiple packets. Each packet is traversing with a different path, but all the packet will reach the same destination. When all the packets are collected in the receiver end, they are assembled to form meaningful information. Difference between TCP and IP. IP, termed as Internet Protocol. Its work is to establish a connection by identifying another computer of the other end and then deliver the packets to the target destination. Internet Protocol identifies another computer through an address system known as an IP address. An IP address is a prime way to identify any computer in the network. But Internet Protocol does only one part of the job. Another part of the job is done through Transmission Control Protocol, TCP. The Transmission Control Protocol handles the ordering and delivery of the packets and manages the error correction during communication. Both TCP and IP assist each other during the transmission of data from source to destination. That's why it is known as TCP over IP, and the whole process is based on a model known as the TCP over IP model. TCP over IP model. The TCP over IP model both defines and references a large collection of protocols that allow computers to communicate. To define a protocol, TCP over IP uses documents called requests for comments, RFC. The TCP over IP model also avoids repeating work already done by some other standards body or vendor consortium by simply referring to standards or protocols created by those groups. The TCP over IP model creates a set of rules that allows us all to take a computer, or mobile device, out of the box, plug in all the right cables, turn it on, and connect to and use the network. You can use a web browser to connect to your favorite website, use most any app, and it all works. How? Well, the operating system on the computer implements parts of the TCP over IP model. The Ethernet card, or wireless LAN card, built into the computer implements some LAN standards referenced by the TCP over IP model. In short, the vendors that created the hardware and software implemented TCP over IP. To help people understand a networking model, each model breaks the functions into a small number of categories called layers. Each layer includes protocols and standards that relate to that category of functions, as shown in figure. The TCP over IP model's main functionalities are based on the theoretical OSI model. In the OSI model, there was a 7-layer, whereas, in the TCP over IP model, it shrinks to 4-layer. The 4-layer of the TCP over IP model includes 1 application layer, 2 transport layer, 3 network layer, 4 data link and physical layer. Here is application layer, transport layer, network layer, data link, and physical layer. Application layer. The application layer of the TCP over IP model contains lots of application layer protocol, and each protocol is used for a different type of communication. To establish network communication for a different purpose, we need a software program or application to follow the application layer protocols. So, the software program or application uses these types of application layer protocols to request different kinds of actions. Some of the standard application layer protocols are HTTP, HTTPS protocol used for web browsing. FTP, TFTP, NFS file transfer protocol. SMTP protocol for sending email messages. POP3 protocol for receiving email messages. IMAP protocol for managing email messages on the server. Telnet, RLogin protocol for accessing remote computers. SNMP protocol for network management. DNS protocol for finding IP address assigned to web addresses. Each of the application layer protocols will have different input data and can generate different queries. All these data are sent to the next layer, which is the transport layer. The transport layer has nothing to do with the content of the application layer, and it will process every data in the same way. HTTP overview. The Hypertext Transfer Protocol, HTTP, is an application-level protocol for distributed, collaborative, hypermedia information systems. HTTP is a generic and stateless protocol which can be used for other purposes as well, using extensions of its request methods, error codes, and headers. Basically, HTTP is a TCP over IP-based communication protocol that is used to deliver data, HTML files, image files, query results, etc., on the World Wide Web. The default port is TCP/80, but other ports can be used as well. It provides a standardized way for computers to communicate with each other. An HTTP client sends a request message to an HTTP server. The server, in turn, returns a response message. In other words, HTTP is a pull protocol. The client pulls information from the server, instead of server pushes information down to the client. You can see in this figure, HTTP clients send request to HTTP server. And in reply, HTTP server send requested page to the HTTP client. To get the web page from HTTP server, at step 1, HTTP client sends a message with an HTTP header. Generally, protocols use headers as a place to put information used by that protocol. This HTTP header includes the request to get a file. The request typically contains the name of the file, home HTML, in this case, or if no file name is mentioned, the web server assumes that client wants the default web page. In first step, web browser send request get home HTML with HTTP header. In second step, HTTP server reply OK. Here is your requested data with HTTP header. In third step, it will more data but this time without HTTP header. At step 2 shows the response from server. The message begins with an HTTP header, with a return code, which means something as simple as OK. At step 3 shows another message from web server to web browser client, but this time without an HTTP header. HTTP transfers the data by sending multiple messages, each with a part of the file. Rather than wasting space by sending repeated HTTP headers that list the same information, these additional messages simply omit the header. Transport layer. The transport layer is the next in the TCP over IP model, which receives a message from the application layer. The transport layer work is to divide the message into multiple small packets and then add a header and send it to the internet layer. Similarly, in the reverse direction, when data is received from the internet layer, it passes to the application layer. The header of the transport layer contains much information along with the port number of the source and target destination. The transport layer uses port numbers to determine what kind of message is inside the packets and which application layer protocol should receive them. The two main transport layer protocol is used in the process are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. The Transmission Control Protocol, in short TCP, is the most common and reliable protocol between two hosts. The most common application layer protocols that use TCP are HTTP, HTTPS, FTP, SMTP, and Telnet. The User Datagram Protocol, in short UDP, is the fast and connectionless protocol. It does not develop any relation with the receiver end, and also it is not reliable like TCP because there is no guarantee your packets would reach the receiver. The most common application layer protocols that use UDP are DNS, DHCP, TFTP, SNMP, VoIP, and RIP. TCP error recovery basics. TCP over IP needs a mechanism to guarantee delivery of data across a network. Because many application layer protocols probably want a way to guarantee delivery of data across a network, the creators of TCP included an error recovery feature. To recover from errors, TCP uses the concept of acknowledgements. Figure below show the basic idea behind how TCP notices lost data and asks the sender to try again. Web server sending a web page to web browser client with HTTP headers and TCP headers. The TCP header shows a sequence number. If network has a problem, and the network fails to send sequence number 2, the client receives message number 1 and 3 but not receive message sequence number 2. The client requests to web server for send sequence number 2 again. Figure shows web server sending a web page to web browser client, using 3 separate messages. Note that this figure shows the same HTTP headers, but it also shows a TCP header. The TCP header shows a sequence number, SEQ, with each message. In this example, the network has a problem, and the network fails to deliver the TCP message, called a segment, with sequence number 2. When client receives messages with sequence numbers 1 and 3, but does not receive a message with sequence number 2, client realizes that message 2 was lost. That realization by client's TCP logic causes client to send a TCP segment back to server, asking server to send message 2 again. Network layer. The Internet layer, also called the network layer, controls the movement of packets around the network boundaries. The Internet layer adds another header to the packet when it is received from the transport layer. The most important fields in the header are the IP address of the source and destination of the two ends. The Internet layer uses some of the most important protocols. The 3 main Internet layer protocols are IP, Internet Protocol. Internet Protocol work is to identify the IP address and responsible for the delivery of the packet to the destination. ARP, Address Resolution Protocol. The Address Resolution Protocol work is to find out the MAC address of the device from the IP address. ICMP, Internet Control Message Protocol. The Internet Control Message Protocol identifies network problem associated with small packets called datagrams, and send back to the sender with an error message. The TCP over IP application and transport layers act like the person sending letters through the postal service. These upper layers work the same way regardless of whether the endpoint host computers are on the same LAN or are separated by the entire internet. To send a message, these upper layers ask the layer below them, the network layer, to deliver the message. If you want to send a letter, the first thing you will write the letter, then you will pack it into envelope and write address on envelope and post into the letter box. The post office read the address and send them to designation. For example, this letter reached to designation using this route. Network layer work like the post office and send all packet to the designation address. The lower layers of the TCP over IP model act more like the postal service to deliver those messages to the correct destinations. To do so, these lower layers must understand the underlying physical network because they must choose how to best deliver the data from one host to another. So, what does this all matter to networking? Well, the network layer of the TCP over IP networking model, primarily defined by the Internet Protocol, IP, works much like the postal service. IP defines that each host computer should have a different IP address, just as the postal service defines addressing that allows unique addresses for each house, apartment, and business. Similarly, IP defines the process of routing so that devices called routers can work like the post office, forwarding packets of data so that they are delivered to the correct destinations. Just as the postal service created the necessary infrastructure to deliver letters, post offices, sorting machines, trucks, planes, and personnel, the network layer defines the details of how a network infrastructure should be created so that the network can deliver data to all computers in the network. Data link and physical layer. The data link layer or physical layer or network access layer is the physical interface between the host computers and the network hardware. This layer is responsible for the transmission of data between two devices of the same network. It handles the network hardware of the computer, which is used for sending or receiving data using the wireless network, Ethernet cable, network interface card, device driver, and so on. Its main focus is to establish communication between the network card and networking hardware. It also defines how the data should be sent in the network, which includes how bits should optically be signaled by network hardware. Data link and physical layers define the protocols and hardware required to deliver data across some physical network. The two work together quite closely. In fact, some standards define both the data link and physical layer functions. The physical layer defines the cabling and energy, for example, electrical signals, that flow over the cables. Focusing on the data link layer for a moment, just like every layer in any networking model, the TCP over IP data link layer provides services to the layer above it in the model, the network layer. When a host's or router's IP process chooses to send an IP packet to another router or host, that host or router then uses link layer details to send that packet to the next host router. Because each layer provides a service to the layer above it. For example, host IP logic chooses to send the IP packet to a nearby router, R1. Figure shows 4 steps of what occurs at the link layer to allow host to send the IP packet to R1. Figure shows 4 steps. The first 2 occur on client, and the last 2 occur on router R1, as follows. Step 1. Client encapsulates the IP packet between an Ethernet header and Ethernet trailer, creating an Ethernet frame. Step 2. Client physically transmits the bits of this Ethernet frame, using electricity flowing over the Ethernet cabling. Client create an IP packet, and add Ethernet header and Ethernet trailer to that packet, and transmit that data. Router receive data and encapsulates the data by removing header and trailer. And R1 receive the packet and send required data to client. Step 3. Router R1 physically receives the electrical signal over a cable and recreates the same bits by interpreting the meaning of the electrical signals. Step 4. Router R1 encapsulates the IP packet from the Ethernet frame by removing and discarding the Ethernet header and trailer. By the end of this process, client and R1 have worked together to deliver the packet from client to router R1. Data encapsulation. The term encapsulation is used to describe a process of adding headers and trailers around some data. This process can be explained with the 4-layer TCP over IP model, with each step describing the role of the layer. The process by which a TCP over IP host sends data can be viewed as following step. The first steps relate to the encapsulation performed by the 4 TCP over IP layers, and the last step is the actual physical transmission of the data by the host. The steps are summarized in the following list. Step 1. For example, here is what happens when you send an email using your favorite email program. The email is sent from the application layer to the transport layer. Step 2. The transport layer encapsulates the data and adds its own header with its own information, such as which port will be used, and passes the data to the internet layer. Step 3. The network layer encapsulates the received data and adds its own header, usually with information about the source and destination IP addresses. The internet layer then passes the data to the network access layer. As you can see in this figure, application layer give data to transport layer. Transport layer add TCP header and give that data to network layer. Network layer add another IP header and give that data to data link layer. Data link layer add both header and trailer and give that data to physical layer. And physical layer transmit the bits. Step 4. The data link layer is the only layer that adds both a header and a trailer. The data is then sent through a physical network link. Step 5. The physical layer encodes a signal onto the medium to transmit the frame. Note that because the application layer often does not need to add a header, the figure does not show a specific application layer header, but the application layer will also at times add a header as well. TCP over IP message. When talking about networking, people use segment, packet, and frame to refer to the messages. Each term has a specific meaning, referring to the headers, and possibly trailers, defined by a particular layer and the data encapsulated following that header. When transport layer at TCP header, we called it segment. When network layer at IP header, we called it packet. And when data link at header and trailer, we called it frame. Segment encapsulated data as defined by the transport layer. Information such as the source and destination ports or sequence and acknowledgement numbers are included in the header. Packet encapsulated data defined by the network layer. A header contains the source and destination IP addresses. Frame encapsulated data defined by the network access layer. A frame can have both a header and a trailer. OSI model. OSI, Open Systems Interconnection, model was created by the International Organization for Standardization, ISO, an international standard-setting body. It was designed to be a reference model for describing the functions of a communication system. The OSI model provides a framework for creating and implementing networking standards and devices and describes how network applications on different computers can communicate through the network media. The OSI model has 7 layers, with each layer describing a different function of data traveling through a network. Here is the graphical representation of these layers. Application layer, presentation layer, session layer, transport layer, network layer, data link layer, and physical layer. OSI networking model. The OSI model has many similarities to the TCP over IP model from a basic conceptual perspective. It has layers, and each layer defines a set of typical networking functions. As with TCP over IP, the OSI layers each refer to multiple protocols and standards that implement the functions specified by each layer. Note that the TCP over IP model in use today, on the right side of the figure, uses the exact same layer names as OSI at the lower layers. The functions generally match as well. In OSI, application presentation and session layer are 3 different layers. But in TCP over IP there is only one application layer. OSI has transport layer. TCP over IP also has transport layer. OSI has network layer. TCP over IP also has network layer. OSI has 2 different layers, data link and physical layer. But in TCP over IP data link and physical work as a single layer. OSI data encapsulation terminology. Like TCP over IP, each OSI layer asks for services from the next lower layer. To provide the services, each layer makes use of a header and possibly a trailer. The lower layer encapsulates the higher layer's data behind a header. OSI uses a more generic term to refer to messages, rather than frame, packet, and segment. OSI uses the term protocol data unit, PDU. A PDU represents the bits that include the headers and trailers for that layer, as well as the encapsulated data. For example, an IP packet, as shown in figure, using OSI terminology, is a PDU, more specifically a layer 3 PDU because IP is a layer 3 protocol. Here is a graphical representation of all the PDUs in the OSI model. Layer 7 PDU add layer 7 header with data and give that data to layer 6. Layer 6 PDU add layer 6 header with data and give that data to layer 5. Layer 5 PDU add layer 5 header with data and give that data to layer 4. Layer 4 PDU add layer 4 header with data and give that data to layer 3. Layer 3 PDU add layer 3 header with data and give that data to layer 2. Layer 2 PDU add layer 2 header with data and give that data to layer 1. Layer 1 PDU add layer 1 header and trailer with data and transmit that data. Thanks for watching. If you have any problem, let me know in comments. Please subscribe to the Star Technology 5G and click on the bell icon.